To derive the third equation of motion, it can be gotten by eliminating the t term between the first two equations. So we've used t to represent time, and the first step from our first equation of motion, which is v equals to u plus at, the first step in getting a new equation by eliminating t. So we have to eliminate t from both the first two equations. So we have to eliminate t, and we have the first equation v equals to u plus at, and we also have s to be equals to ut plus half at squared, where s represents displacement. So, and in solving this, we would have to square both sides of our first equation, and this will be v squared equals to u plus at squared. And in doing this will now be v squared equals to u plus at multiplied by itself, because any number or any alphabet squared, we multiply it by itself. So that will be u plus at multiplying itself. And in doing this is expansion in algebra, and we'll have we pick the first term multiplying the whole of this, and this will be u plus at, and we'll pick the second term. The second term is plus 80, so plus 80 will be multiplying the whole of this, and this will be, and so solving this further, we have u squared, u multiplied by u squared plus aut plus aut plus a squared t squared, because a multiplied by a squared, t multiplied by t squared. So we simplify this first, and this will be v squared equals to u squared plus, because these are like terms, they can add up together, and this will be 2aut plus a squared t squared. So we try and factor out 2a from the last two terms. So from here we factor out 2a from the last two terms, and by doing that is as if we're finding the HCF of these two terms. This is the first term, 2a ut, and we have a squared t squared. That's the second term, and by doing that, if we factor it out correctly, we're going to have v squared equals to u squared plus 2a into bracket ut plus half at squared. If you look at this, if you multiply this, if you want to remove the bracket, this will be 2aut, and if you multiply it, 2 will cancel out this 2, and we'll be having a left, and a multiplied by a will give us a squared. So the HCF of these two terms is 2a. So, and we've done that correctly. And if you recall, this is our ut plus half at squared is the same thing as s, so we're going to replace that. And if we replace that, we're going to successfully eliminate t from the first equation, and we'll now have v squared equals to u squared plus 2as. So this whole term ut plus half at squared is the same thing as s, which is representing our displacement. So this is it, s. So it represents s this whole term. So and this gives us a new equation, which is our third equation of motion. So this is our third equation of motion. Right equation in short of motion. We can also solve for our third equation of motion by using another method in getting our third equation of motion. We can use this method, or let me write it. You can recall that displacement is equals to average velocity multiplied by time. Because if you look at our average velocity formula, average velocity is equals to displacement over time. And if we want to try and make displacement subject of formula, we'll cross multiply, and this will be our answer. So, and we can also remember that average velocity, that important formula we got, average velocity of a uniformly accelerated motion is equal to initial and final velocity, the sum of two of them, divided by 2. And from our time, and from the first equation of motion, which is v equals to u plus at, if we make t the subject of formula, so let me note it, displacement subject of formula. You also make our time t the subject of formula. Then we have t to be equals to v minus u all over a. So all what we're going to do here now in this second method, in proving for the third equation of motion, we'll come back to our displacement, and we can remember that we represented displacement with s. So s is equals to, so what's our average velocity? We begin to substitute this term. So our average velocity is v plus u over 2 multiplied by time, and we have a relationship here for time, which is v minus u all over a. So what we do here, we multiply, and when we multiply this is going to give us v multiply v plus u multiplying v minus u all over 2a. I can easily deduce that this is difference of two squares. This is a relationship, difference of two squares. In mathematics, we have this to be difference of two squares. But solving this by multiplying would give us the formula of the difference of two squares. And if I expand this correctly and I'll solve that, I will have this first term multiplying the whole of this. This will be v into bracket v minus u, and plus u multiplying this term v minus u all over 2a, and this will be equals to, let me equate it here. So this will be v squared minus uv plus uv plus u squared. Because if you look at it, plus u times v will give me plus uv, and two opposite sign will give me a negative sign rather. So this should be minus u squared. So, and this will cancel out because minus uv plus uv will cancel out, they are the same thing, and all I'm left with would be all over 2a, and this will be s is now equals to v squared minus u squared all over 2a. So we can see that this is the same thing of difference of two squares. So from here, all what I'll do would be to cross multiply from here. When I cross multiply, this will be all of this term multiplied by 1 will give me v squared minus u squared equals to 2as. And to make v squared stand alone, I'll take this to the other side, or I add both sides by plus u squared to cancel this out, and this will be v squared is equals to u squared. When I bring this will be positive u squared plus 2as. And so we can see that we have the same formula as the one above for the third equation of motion. So we have obtained equations of motion in a straight line or in a specific direction, also called rectilinear motion, which can be said to be under uniform acceleration. So we have the three major equations of motion here, and we can see a useful formula that is important when you're considering cases of uniformly accelerated motion.